why your phone gets warm, how we might build these incredibly tiny quantum computers. Today, we're taking a deep dive into the fascinating world of phonons, these quantum packets of sound and vibration that, well, ripple through pretty much every solid material around us.
What's truly wild here, I think, is how these tiny sort of emergent entities perfectly illustrate one of quantum physics' deepest mysteries, wave-particle duality.
Right.
Our source material today is Phonon Duality, waves, particles, and quantum technology, which really digs into the de Broglie wavelength of phonons and its, well, frankly, mind-bending implications.
So our mission then is to understand how something that's essentially a vibration can act like both a wave and a particle.
Exactly.
Yeah.
And why that distinction matters for everything from, like you said, the heat in your laptop to the actual future of quantum tech.
Okay, let's start with the basics of that duality. Because back in the early 20th century, physics was completely, upended.
Right.
We realized light, which we thought was purely a wave, also behaves like particles, photons.
Mm-hmm.
And then, conversely, particles like electrons surprisingly started acting like waves. The key insight here is that any particle with momentum has an associated wavelength, a concept formalized by Louis-Victor de Broglie back in 1924.
Yeah, he gave us that famous relationship. Lambda, the wavelength, equals Planck's constant h divided by momentum, p.
Simple but profound.
Exactly. For big, everyday objects, their mass is so huge that this de Broglie wavelength is just immeasurably tiny, so we never notice their wave nature. But for microscopic particles, it's very real.
Like electrons.
Think about electrons. The audacious prediction that they could behave like waves was spectacularly confirmed in, 1927? By Davisson and Germer.
Right, with the nickel crystal experiment.
Yeah, they essentially bounced electron beams off it and saw a diffraction pattern.
Yeah.
I mean, that's a definitive sign of wave behavior.
And this wasn't just like a cool finding, was it? It changed things.
Oh, fundamentally. It paved the way for understanding Niels Bohr's quantized energy levels in atoms, imagining electron orbits as standing waves.
Yeah.
And it really laid the groundwork for Schrodinger's wave mechanics.
That makes perfect sense for individual electrons, but
Yeah.
how do we jump from these tiny particles to something as complex as a solid? Full of vibrating atoms. How does wave-particle duality play out there?
That's exactly where phonons come in. So imagine a crystalline solid, like a diamond or a metal, not as static atoms, but as this vast interconnected network of atoms constantly jiggling and vibrating due to thermal energy.
Okay.
Classically, we just describe these as collective vibrational waves propagating through the crystal, just like sound waves.
Right.
But quantum mechanics takes these mechanical lattice waves and, well, it quantizes them into discrete energy packets.
Ah, like photons for light.
Precisely. Much like electromagnetic waves are quantized into photons, these vibrational energy packets are called phonons. The term was suggested by Yakov Frankl, deriving from the Greek phone for sound to highlight that analogy.
Okay, so if I'm getting this right, these aren't fundamental particles like electrons or photons.
No, that's a key distinction.
So why do we call them quasiparticles? What does that really mean for us?
It's basically a powerful simplification. I mean, think about it. Tracking 10 to the 23 interacting atoms in a crystal is just impossible.
Right.
The quasiparticle concept transforms this massively complex problem into a much more manageable one.
Yeah.
A smaller number of, let's say, weakly interacting phonons.
Okay, so it's a model.
A very effective one. And these collective vibrations, they manifest in distinct types. First, you have acoustic phonons. These involve neighboring atoms moving in sync, kind of like a macroscopic sound wave.
Like a ripple going through.
Exactly. For long wavelengths, their frequency is directly related to their wave motion, and they're responsible for thermal transport and actual sound. They can move back and forth, longitudinally, or side-to-side transversely.
Okay. And the other type?
Then there are optical phonons. These only exist in crystals with 2 or more atoms in each repeating structural unit, the unit cell.
Right.
Here, atoms within that unit move out of phase, sort of against each other. This creates a fluctuating electrical charge, an oscillating dipole moment, which lets them interact strongly with infrared light, hence the name optical.
Ah, makes sense.
And unlike acoustic phonons, optical phonons have a sort of minimum energy, a finite frequency, even when their wavelength is really long, what physicists call the center of the Brillouin zone.
Okay, so if a phonon is considered a particle, even a quasiparticle, it must have momentum, but like a crystal isn't physically moving through space when its atoms vibrate. So what kind of momentum are we actually talking about here?
That brings up a really crucial point. For phonons, We use the term crystal momentum, or quasi-momentum, often written as h bar k.
Okay.
And it's paramount to distinguish this from true Newtonian mechanical momentum, PMV.
Like a baseball.
Exactly. The total mechanical momentum of all atoms in a crystal that contains a single phonon is actually zero.
Huh. So where does this crystal momentum come from?
It arises from the discrete, repeating pattern of the crystal lattice itself, for its symmetry. While regular linear momentum isn't conserved in a crystal because it doesn't have continuous symmetry, crystal momentum is conserved in interactions within the crystal.
With a catch.
With a catch, yes. It's conserved modulo, a reciprocal lattice vector, which is a fancy way of saying it resets periodically because of the lattice structure. But still, it's an indispensable tool for analyzing how things scatter and interact inside a solid.
Okay, so with this crystal momentum in hand, we can formally apply the de Broglie relation to a phonon. Its wavelength is basically 2 divided by its wave vector k. So we're treating this collective vibration as a single entity with both particle-like properties like quantized energy and this conserved crystal momentum and wave-like properties like frequency and wavelength. But is this dual picture always accurate? Does it ever break down?
This is where it gets really interesting. The validity of this simple phonon model isn't absolute. It relies heavily on what we call the harmonic approximation.
Meaning
Meaning we treat the forces between atoms like perfect linear springs, like Hooke's law.
Okay, but reality isn't always perfect springs.
Exactly. When atomic displacements become large, or maybe at high temperatures, and harmonicity becomes significant, the forces aren't perfectly linear anymore.
That messes things up.
It leads to strong phonon interactions. Phonons start bumping into each other more. This gives phonons a finite lifetime. They don't last forever, and the simple quasi-particle picture starts to break down. It can also get tricky near structural phase transitions, where a particular phonon mode might soften, losing its well-defined energy and lifetime.
So the de Broglie wave model for a phonon is most accurate and predictive at, say, low temperatures and when the crystal is stable.
That's generally true, yes. And the fascinating conceptual loop here is that the phonon's wavelength is related to a momentum that exists because the medium it's propagating in is this ordered wave-like array of atoms.
Huh.
It truly underscores that the phonon is an emergent property of the crystal itself. It's not separate from it.
So this theoretical framework sounds incredibly powerful, but how do we actually see these phonon waves? How do we, prove their existence and measure these properties in a lab?
Well, the most definitive evidence for the wave nature of phonons comes from measuring their dispersion relations.
Okay, what are those exactly?
They're essentially maps. They show the relationship between a phonon's energy, or frequency, and its crystal momentum, or wave vector. Plotting this out gives you a curve.
And that curve tells you?
A lot. Bertram Brockhaus pioneered this, actually won a Nobel Prize for it, and opened up the whole field of phonon spectroscopy. The unique shape of a material's dispersion curve is like its fingerprint. It reveals crucial details: acoustic versus optical branches, the speed of sound in the material, how stiff it is, the group velocity, the phonon density of states, all critical for calculating things like specific heat and thermal conductivity.
For decades, the gold standard for measuring this has been inelastic neutron scattering, or INS. Why neutrons? What makes them so special for this kind of work?
It's really due to a fortunate coincidence of scales. It turns out that thermal neutrons, basically neutrons slowed down to room temperature energies, have energies and de Broglie wavelengths that are just perfectly matched to the typical energies and interatomic spacings of phonons and crystals.
A perfect match.
Pretty much. This allows for a single measurable scattering event where a neutron comes in, hits the sample, and creates or absorbs a single phonon.
And you can measure the change.
Exactly. It's governed by 2 fundamental conservation laws: conservation of energy and conservation of crystal momentum. Instruments like the triple-axis spectrometer were designed specifically to meticulously map out that dispersion curve, point by point.
That's truly amazing, a perfect tool match. But what are the limitations of INS? I mean, science always pushes boundaries, right? How has technology stepped up?
Yeah, while incredibly powerful, INS does have its drawbacks. It typically requires quite large samples, maybe centimeter-sized, which can be a real problem for new exotic materials that we can only synthesize in tiny amounts.
Okay.
And it can also struggle with magnetic interference, since neutrons themselves have a magnetic moment and interact with magnetic fields in the sample. This created a kind of bottleneck for studying many novel materials.
So what came next?
In recent decades, high-resolution inelastic X-ray scattering, or IXS, has emerged as a really powerful complement, or sometimes alternative.
Okay, using X-rays instead.
Right. The principle is similar. X-rays scatter inelastically from the sample, creating or annihilating a phonon. But it faces a monumental technical challenge.
Which is?
You're trying to detect the tiny energy changes caused by phonons, maybe milli-electron volts, from X-rays that have energies in the kilo-electron volt range.
Yeah.
That's like trying to measure the height change of a single blade of grass on top of Mount Everest.
Wow.
It requires extraordinary energy resolution on the order of like 1 part in 10 million or even 1 part in 100 million.
So despite that huge technical difficulty, what are the advantages? Why go to all that trouble? What makes IXS such a game changer?
Well, IXS offers several key advantages that make tackling that technical hurdle absolutely worth it. First, it can be performed on extremely small samples.
Small.
We're talking micrographs or single crystals with diameters as tiny as 10 to 100 micrometers. This is transformative for studying new materials synthesized in small quantities or materials under extreme conditions like high pressure inside diamond anvil cells.
Huge advantage.
Definitely. Second, X-rays don't have the same kinematic restrictions as neutrons. This means IXS can easily probe very high-energy phonons or materials where sound travels incredibly fast, which can be difficult for INS.
Okay.
Third, X-rays interact primarily with electrons, unlike neutrons which interact with atomic nuclei and magnetic moments. This makes IXS ideal for studying phonons and materials with strong magnetic behavior.
Was that?
Because in INS, the magnetic scattering signal could just completely overwhelm the weaker phonon signal. A good example is the heavy fermion compound Ur2Si2. Very hard to study its phonons with neutrons because of the magnetism, but IXS works well.
So it opens up new classes of material.
Precisely. And of course, we also have other techniques like Raman and Brillouin scattering, but they're generally limited to probing phonons only with very long wavelengths near the zone center.
So it really shows that feedback loop.
Mm-hmm.
Theory predicts, experiments hit limits, technology innovates.
Exactly. And that innovation overcomes the bottlenecks, opening new frontiers, allowing more rigorous tests of theories, and leading to discoveries of new phenomena. Is how science progresses.
Okay, so we can describe phonons, we can measure them with these amazing techniques, but for someone who isn't a solid-state physicist, why should we really care about this wave-particle duality? What are the tangible, real-world implications?
That's a crucial question because this isn't just abstract physics. It has profound and measurable consequences for the actual physical properties of materials we use every day. Let's start with heat conduction or thermal transport.
Right, like the warm phone example.
Exactly. In large macroscopic materials, heat conduction is typically described by Fourier's law, basically treating phonons like little particles scattering randomly off each other and imperfections, diffusing heat.
The classical picture.
The classical picture. But in nanomaterials, think incredibly thin films or tiny nanowires, things get, well, wild. When the physical dimensions of the system become comparable to, or even smaller than, the phonon wavelength, or how far a phonon can travel before scattering, its mean free path, that classical particle picture just breaks down.
So we're talking about different ways heat can move through materials, totally depending on their size and structure. Tell us about these different regimes.
Yes, there are basically three main regimes to think about. First, there's diffusive transport. This is the classical particle-like picture we just mentioned. The phonon mean free path and wavelength are much smaller than the system size. Heat spreads out, and thermal conductivity is an intrinsic material property.
Like in a big block of metal.
Pretty much. Then you have ballistic transport. This happens when the system size is smaller than the phonon mean free path.
So they don't scatter.
Right, phonons can essentially zip straight through the material without hitting anything. Heat flow in this regime is determined more by the number of available phonon modes and their transmission probability, like how easily they can get from one side to the other. We see evidence of this in materials like specially oriented polyethylene, where heat conducts unusually well along the aligned polymer chains.
Okay, diffusive and ballistic. What's the third?
The third, and maybe the most interesting from a duality perspective, is coherent wave-like transport. This is where the phonon's wave nature truly takes center stage.
Ah, the interference effect.
Exactly. When phonons with long wavelengths encounter a precisely engineered repeating nanostructure like a superlattice, which is a repeating stack of ultra-thin layers of different materials, their waves can interfere with themselves, constructively or destructively.
Like light waves through a grating.
Precisely analogous. This fundamentally alters their vibrational properties and can lead to phononic band gaps.
Band gaps for sound or heat.
Yes. Think of these as specific frequency ranges, where phonons simply cannot propagate through the structure. It's like a forbidden zone for those particular vibrations.
So, wait, if these waves can interfere and create forbidden zones, does that mean we could actually design materials to block or filter heat in specific ways? Could we build like a heat wall or a heat filter by exploiting this wave nature?
Precisely. That's exactly the idea. This understanding provides an incredibly powerful toolkit for thermal engineering. For instance, think about thermoelectric devices.
They convert heat into electricity, right?
Right, or vice versa.
Yeah.
For efficient heat to electricity conversion, you actually want very low thermal conductivity on one side so the heat doesn't just leak away across the device.
You want to maintain the temperature difference.
Exactly. By designing superlattices with specific precise periodicities, we can leverage these coherent phonon wave effects, the interference, to selectively scatter the main heat-carrying phonons and significantly reduce the overall heat flow.
Has this been demonstrated?
Oh, yes. Studies on oxide superlattices like lanthanum cobalt oxide strontium titanate, LaCo3SRTO3, have clearly shown that even slight variations in the layer periodicity can disrupt phonon coherence and allow you to precisely tune the thermal conductivity. It opens a really practical path to designing advanced thermal management materials from the ground up.
Okay, that's absolutely fascinating, using the phonon's wave nature to impede heat flow. But here's where my mind really starts bending. The particle-like nature of phonons is apparently fundamental to enabling perfect charge transport in conventional superconductivity.
Isn't that something? This may be the most stunning example of their functional duality, the landmark Bardeen-Cooper-Schrieffer BCS theory.
The Nobel Prize-winning theory for superconductivity.
That's the one. It explains conventional superconductivity as this amazing macroscopic quantum phenomenon that arises from an effective, attractive interaction between electrons. Which is weird because electrons normally repel each other, right?
Right, Coulomb repulsion, like charges repel.
Exactly. But BCS theory says this attraction is mediated by the exchange of virtual phonons.
Okay, unpack virtual phonons.
So imagine one electron moving through the crystal lattice. Its negative charge attracts the nearby positive ions in the lattice, causing a slight distortion, a local compression or ripple in the lattice structure.
Like a wake behind a boat.
That's a decent analogy.
Yeah.
This distortion, this region of slightly enhanced positive charge due to the bunched-up ions, can be described as a cloud of virtual phonons. It persists for just a tiny fraction of a second after the first electron has passed.
And then
A second electron, coming along behind the first one, is attracted to this region of enhanced positive charge. So the net effect is an indirect, slightly delayed attraction between the two electrons, mediated by the lattice vibration, the phonon.
Wow. So the phonon acts like a messenger carrying an attractive force between electrons.
In essence, yes. It's a quantum mechanical exchange force.
And these interacting electrons form what we call Cooper pairs, right? Yep.
Exactly. If this phonon-mediated attraction is strong enough to overcome the direct Coulomb repulsion, electrons can form these bound states called Cooper pairs, typically two electrons with opposite momenta and opposite spins.
And why is that pairing so important?
Because a Cooper pair, having integer spin, zero spin usually, behaves like a boson, not a fermion.
Ah, so they don't have to obey the Pauli exclusion principle.
Correct. This means that all the Cooper pairs in the material can condense into a single coherent macroscopic quantum state, the BCS ground state. And it's this coherent state that allows for zero electrical resistance and the expulsion of magnetic fields, the famous Meissner effect.
And the strength of this electron-phonon interaction, the glue, determines how good a superconductor it is.
Absolutely. The strength of this electron-phonon coupling directly determines the critical temperature, T(C), below which a material becomes superconducting. Stronger coupling generally means a higher Tc.
And the definitive experimental proof for the phonon's role was
the isotope effect. This was a crucial discovery. If you take a superconducting element, say mercury, and replace the common isotope with a heavier one, the critical temperature decreases.
Why?
Because the heavier ions vibrate more slowly, the phonon frequencies are lower. The fact that Tc depends on the isotopic mass, Tc proportional to m to the power of negative alpha, usually around negative 0.5, was incredibly strong evidence that lattice vibrations, phonons, were indeed the mechanism mediating the electron pairing.
This is just mind-blowing, so let me see if I have this straight. The phonon's wave nature is used to build barriers, like in those superlattices, to block heat flow, while its particle nature, acting as that exchange particle, is used to build perfect conduits for electricity in superconductors.
That's a fantastic way to put it. It's a functional duality that's genuinely profound. The same entity, viewed through its wave or particle lens, enables completely different, almost opposite functionalities.
Okay, this level of understanding and increasingly control over phonons is fueling a whole new field you mentioned earlier, phononics. What kind of exciting technological frontiers are opening up now that we can manipulate sound and heat at this quantum level?
Yeah, phononics is really taking off. It's all about trying to control sound and heat flow with the same kind of precision that electronics controls charge or photonics controls light. It's about engineering with phonons.
So what are the big areas?
Well, one major area is quantum acoustics. This field is really ambitious. It aims for control at the single phonon level.
Wow.
It involves treating phonons with the same quantum mechanical formalism we use for photons in quantum optics. Researchers are developing these fascinating hybrid quantum systems,
Hybrid meaning?
meaning they connect different types of quantum systems together. For instance, coupling tiny mechanical resonators, think microscopic tuning forks or drumheads, to superconducting qubits, which are a leading platform for quantum computing.
And the phonons do what in this setup?
These phonons, these quantized vibrations in the mechanical resonator, can actually store quantum information, they can help process it, or they can act as a transducer, converting quantum information between the electrical qubit and, say, microwave photons.
And I heard these mechanical resonators have some potentially serious advantages for quantum technology, don't they?
They absolutely do. One huge factor is size. Remember, sound travels vastly slower than light, like 100,000 times slower.
Right.
This means that an acoustic cavity, or resonator, designed for a specific frequency can be about 100,000 times smaller than an electromagnetic cavity for the same frequency.
That's a massive difference for scalability.
Huge. It offers significant advantages if you're trying to pack lots of quantum components onto a chip. Plus, nanomechanical resonators can be fabricated with incredibly high-quality factors, or Q factors.
Meaning they ring for a long time.
Exactly. They lose energy very, very slowly. This translates into exceptionally long coherence times for the quantum states stored in them, sometimes on the order of seconds, which is an eternity in the quantum world. This makes them highly attractive for building robust quantum memories.
Okay, quantum acoustics. What else falls under phononics?
Another really exciting area is phononic crystals and metamaterials. We touched on this with the superlattices for heat control.
Right, the engineered structures.
Exactly. These are materials engineered with a periodic variation in their acoustic properties, density, stiffness on the scale of the phonon wavelength. This allows really unprecedented control over how sound and heat flow. As we discussed, this creates those phononic band gaps.
The forbidden frequency ranges.
Right. Specific frequency ranges where phonons just cannot propagate through the structure.
So beyond just basic thermal insulation or filtering heat, what else can these band gaps enable? What kinds of devices could we actually build with them?
Well, by carefully tailoring these band gaps and the structure, we can create active phononic devices. Imagine things like thermal diodes.
Like an electrical diode, but for heat?
Precisely. Allows heat to flow easily in one direction, but blocks it in the other. Or even thermal transistors, which could potentially switch or amplify heat currents, forming the basic building blocks for thermal circuits computing with heat, essentially.
Wow.
They also offer a potentially revolutionary approach to vibration and noise control, especially for difficult low-frequency noise that conventional materials struggle to absorb or block.
And you mentioned sensors.
Yes, their ability to guide and focus acoustic energy, or to be exquisitely sensitive to changes in their environment, makes them very promising for developing ultra-sensitive sensors, or maybe even for efficient energy harvesting from ambient vibrations.
Okay, and the most ambitious frontier you mentioned, the idea of actually replacing electrons with phonons in computers. That still sounds like science fiction.
It's definitely a bold, long-term vision, phononic circuits and nanomechanical computing.
What's the motivation there? Why even try?
Well, the potential payoff is huge. Imagine computing devices that are incredibly robust. They could potentially operate in harsh environments, like high temperatures or radiation, where electronics fail. And perhaps more importantly, they might offer fundamentally lower energy consumption compared to electronics.
So what would the basic building blocks look like?
You'd need analogs to electronic components, so phononic waveguides to act like wires carrying the phonon signals. Nanomechanical resonators would likely be the core processing or memory elements. You'd need to exploit phenomena like B-stability,
Meaning?
where a resonator can vibrate stably at two different amplitudes.
Yeah.
You could assign one amplitude to be a logical 0 and the other to be a 1.
Okay, like a switch.
Kind of. You'd also need things like acoustic tunnel barriers for controlled coupling between these elements, letting signals pass or be blocked. And crucially, you need ways to read out the state optomechanical readout. Using light to non-invasively measure the mechanical state is a common approach.
And have there been real experimental breakthroughs here, or is it still mostly theoretical?
Oh, there have been significant strides experimentally. Researchers have successfully demonstrated reprogrammable nanomechanical logic gates, things like A&D or NAND, NOR gates, where the logical state is indeed defined by the divisible vibrational amplitude of one of these nonlinear resonators.
That's actual logic operation using mechanics.
Exactly. And a really crucial breakthrough recently has been developing gates that are driven acoustically and operate at a single frequency. This is key because it allows the output vibration of one gate to potentially serve as the input vibration for the next gate.
Which is essential for building larger scalable circuits, right? Like connecting transistors together.
Precisely. It's a huge step towards making phononic circuits a practical possibility, even if it's still early days.
So looking ahead, is the future purely phononic? Or is it more likely to be a team effort, maybe combining phonons with electronics and photonics?
I think the latter is much more likely and probably more powerful. It probably points not toward a wholesale replacement of electronics, but rather toward hybrid electronic phononic systems.
Leveraging the best of all worlds.
Exactly. Phonons are almost never manipulated in complete isolation anyway. Their greatest potential often lies in their ability to couple strongly and usefully to other physical systems. Quantum acoustics, as we said, relies on coupling phonons to electronic qubits. Advanced phononic circuits are often designed with optomechanical interfaces for readout and control using light.
So they work together.
Right. There are projects like the INPAO project, for example, explicitly aiming to build integrated nonlinear phononic circuits with optomechanical interface for combined electronic phononic technologies. It's a powerful collaborative hybrid vision for the future where different types of quantum excitations, electrons, photons, phonons, all work together.
So wrapping this up, what does this all mean for us? The journey of this phonon concept, starting as just a theoretical tool to explain things like heat capacity, and now becoming this controllable quantum entity, it's truly remarkable.
It really is.
This deep dive has shown us how applying this fundamental idea of wave-particle duality to these collective quasiparticles hasn't just reshaped our basic understanding of the material world, but is now genuinely paving the way for potentially transformative technologies. We've seen its incredible functional duality, its wave nature exploited to build barriers against heat, and its particle nature harnessed to build perfect conduits for electricity. It's amazing.
It really is. And the ability to precisely command the flow of heat and sound, essentially engineering vibrations at the quantum level, promises this whole new era of materials by design. Of course, challenges remain big ones, like mitigating decoherence, noise in quantum phononic systems, and achieving scalable, reliable fabrication.
And practical hurdles.
Right. But the opportunities are just vast. The sound of atoms vibrating in a crystal, which we used to think of mostly as just unwanted thermal noise, is now being orchestrated quite literally, into a symphony of new physics and potential technology.
A symphony of vibrations.
Exactly. And by listening carefully to this symphony, using the lens of wave-particle duality, we continue to uncover some of the most subtle, powerful, and potentially useful phenomena hidden within the material world. It really makes you wonder, doesn't it? What other hidden symphonies are waiting to be uncovered in the seemingly ordinary materials all around us if we just find the right quantum lens to view them through?